All right, I'm back. Sorry about that interruption. So, reminder, the Reynolds number is a comparison of the separation forces to the cohesive forces. So, there's a Reynolds number for every different geometry. The geometry we did earlier in the semester was flat plate. There's also a Reynolds number for pipe flow, which is again symbolized R, E at D. A factor which contributes to making turbulence likely would be in the numerator, and a factor which inhibits turbulence would be in the denominator. So, taking a look at our most basic formula for the Reynolds number, it is going through some of the factors. Mass flow rate, the more mass that's trying to squeeze through this pipe, the more likely it's turbulent. So that's m dot is in the numerator. Okay. How about viscosity? That impedes turbulence, makes it more likely that we get laminar smooth flow, so viscosity is in the denominator. Okay. How about diameter of the pipe? It's often just symbolized by a D without the subscript I, but it does stand for the inner diameter of the pipe. Right? And the bigger the pipe is, the less the frictional effects and the more likely it's going to be laminar. So D is in the denominator. Okay. And there's a couple factors in there that we can derive from another equation. All right, so there is one of our two basic equations for the Reynolds number. It gives us a likelihood that we're going to have turbulence. It gives essentially a measure of the degree of turbulence of flow within a pipe for m dot pi mu d. This is for fully developed flow, or that's actually what we're going to use in this class. All right, a couple other relationships that you should know for pipe flow. We are interested in how fast a fluid is moving, and this is the book symbol for average speed. Remember, the fluid was stopped at the edges and flowing faster in the middle. So average speed or bulk speed. So giving you a couple formulas that you should know, okay? The average speed we can get by taking the volumetric flow rate and dividing it by the cross-sectional area of the pipe it's flowing through. So average speed, volumetric flow rate divided by cross-sectional area. Right? In addition, earlier in the unit we said, hey, how do we figure out mass flow rate if we have volumetric flow rate? So for example, if this here were meters cubed per second and we want kilograms per second, we would take meters cubed per second and multiply it by kilograms per meter cubed, which is the density of the fluid. All right, and of course, since density is 1 over specific volume, we can write that formula as well. All right, putting some things together, some other relationships that end up being useful. We can get our mass flow rate by taking our average speed and multiplying it by a cross-sectional area. Okay, average speed times cross-sectional area is going to give us our volumetric flow rate. You can see that from this relationship right here, and then multiply it by our density. Okay. And then if we end up combining this formula right here with that formula here, we get an alternate expression for the Reynolds number. So the Reynolds number is going to, it turns out you can crank through this yourself, the average speed times the density times the diameter divided by the viscosity. All right. So all these equations up here are important, things that you can work with in various situations. You should have them all. Just another note before we get going and work through an example. It's an amazing thing that these formulas provide a measure of turbulence for any fluid: engine oil, water, ammonia, air, glycerin, etc. So, and that expression accurately predicts whether things will be turbulent or not. All right, give me a second just to erase the board, and we'll get a quick example up there where we're going to calculate the Reynolds number. I encourage you to pull out your tables and get the data that you need from the tables so that you get some practice with that. That is what you will need to do on test 3. What I'm going to do is do a pipe similar to the pipe that I had earlier. This 3/4 inch copper pipe, that's about 2 centimeters inner diameter, so roughly speaking. And so we're going to imagine we have a small pipe with 2 centimeter diameter, okay? And we're going to have fully developed flow within that pipe. We're going to have some fluid coming in with speed 10 meters per second. Excuse me. and we're going to have the fluid come in at a cool temperature and go out at a warm temperature. Okay, and our questions are, hey, what's the Reynolds number and is it turbulent? What is the Reynolds number and is it turbulent? All right, well, obviously to do that you need the properties, and the convention is to look up at the properties at the average temperature at the inlet or in the outlet. So take properties at the average temperature at the inlet and the outlet. These would be mean temperatures, mean fluid or bulk fluid temperatures. So that idea is expressed as follows. Okay, look up those temperatures at the mean fluid at the average of the inlet and the outlet temperature, which in this case we've made the numbers easy. 11 plus 43 is 54, over 2 is 27, so we're going to look at properties at 27 degrees C. All right, so let me just set up a quick chart for you. Well, let's do air and engine oil. Let's say we have air. We're trying to squeeze air through a 2-centimeter pipe, 10 meters per second. It's going 10 meters per second. Is it going to be laminar or turbulent? And we'll do the same thing for engine oil. So a quick chart. F is going to stand for our fluid. Okay, we'll do air. Okay, and we're going to do engine oil. All right. To do these calculations, if you have the Reynolds number, you'd be saying, oh, okay, I need to know the viscosity and I need to know the density. And those are important factors. So what I would encourage you to do is go ahead and look up your viscosity and look up your density. Okay. And then we're going to do 2 quick calculations. We're going to get the mass flow rate. Actually, let's just go ahead and get the Reynolds number and see how it turns out. That'll be good enough. So we're going to get the Reynolds number. Okay, and we could do the mass flow rate from our equations, but we'll do that second formula where we take the average velocity, we multiply by the density, we multiply by the pipe diameter, and we can divide by the viscosity. All right, so you might want to pause it and do those calculations yourself and take a look at the difference between the two. Okay, hang on for just a second, please.